So we're going to be looking at the end of Hellenistic mathematics. This is sort of the beginnings of trigonometry. We're going to focus on two mathematicians, Hipparchus and Ptolemy. Now, they were motivated in part by making astronomical observations. And if you have a model of the universe, it says you're the center of the universe and everything is rotating around it, which obviously isn't true, but it makes sense, and these things are still used. Then you need to be able to do some sort of spherical trigonometry, measure angles like this and that sort of thing. Okay, but to be able to do that, you really need to be able to do trigonometry in the plane, and so that's what we're going to look at. We're going to look at parts of the, and other things, but with respect to Hipparchus and Ptolemy, we're just going to look at what they did for the plane trigonometry. That is, trigonometry in the plane. We're going to begin with a circle here. For some reason, I erased the center of the circle. Hopefully it's approximately here. The standard that they used was that the radius of the circle is equal to 60, but I'm just going to say the radius of the circle is equal to r. And they divided the circle. Hipparchus, I think, was the first one to do this, divided it into 360 degrees. In a base 10 system, that might not make a whole lot of sense, but in a base 60 system, I think it makes a little more sense because this is represented as 6, 0 in a base 60 system, which just makes more sense than it does in a base 10 system. In addition to that, recall that the standard thing is to divide every degree into 60 units called minutes, and then divide every minute into 60 units called seconds. Okay, well, why are we dividing them into 60ths rather than tenths? And again, this is just a base 60 thing. This really does make a lot of sense if you're dealing with base 60, because a minute then is 1/60th of a degree. And so if, like, a degree is a unit, a 60th of that is going to be like the first, like in the fractional sexagesimal expansion, is, we would call it decimal. That is everything to the right of the decimal point, be everything to the right of the sexagesimal point. That first number is going to be that number times 1/60. And then the second number is going to be that number times 1/60 squared. But those are just seconds. Those are just minutes and seconds. So in other words, what I'm saying here is that if you do a fractional sexagesimal expansion, that first digit, okay, is going to be the number of minutes, and that second digit is going to be the number of seconds, because a second is 1/60th squared of a minute, and a second is 1/60th squared of a degree, and a minute is 1/60th of a degree. And that's how the expansion goes to the right of the decimal place. It's 1/60, the number times 1/60th plus the number times 1/60th squared, and so on and so forth. Okay, and so this is how you'll notice that when the book makes these measurements with angles and stuff like that, it'll give it as a number followed by a semicolon followed by a number followed by a column. That first number is the number of degrees. Okay, that's written that's the base 10 number of degrees, and then that first number is the number of minutes written in base 10, and that second number is the number of seconds written in base 10. Okay, so it's a little bit confusing because we're writing things in base 10, but it's all the reason we're writing it like this instead of like in decimals and parts of 10 is going to be based on the fact that they were dealing with base 60 system. This does look like it should be I think this one, that might be a little bit closer to the center. Okay, but for us, I'm just going to deal with the radius being r. All right, now the fundamental building block, or the fundamental function, they didn't call it that, but the fundamental thing that they dealt with is the chord function. And when I think of trigonometry, I think sine and cosine, that sort of thing. The chord function is what existed before they were using sine and cosine regularly like we are. And I'll say what the chord function is now. So let me first just draw a dashed line. This is kind of like the horizontal axis, the x-axis that we might call in modern day terms, but we don't really need to think of it in terms of that. I just want to make sure everybody knows what I'm talking about here. I'm going to draw an angle here. And my goal now is I want to draw an angle that's basically going to be, I want this angle and this angle to be the same. So something roughly like this. So this whole angle right here is alpha, and then just this angle here is going to be alpha over 2, which of course means that angle there also has to be alpha over 2. I'm going to label this point here B, and this point here C, and chord alpha is just the chord going from B to C. So it's equal to BC. And following along with what the book and other people do, I will use BC and various things to represent both the line segment and its length. So the chord of alpha is equal to BC. Okay, so let's think about how the chord function is related to our modern sine function. Well, notice that this distance here, that's the radius, so that's r. If I look at this distance here, and I want to compute sine of alpha over 2, what is sine of alpha over 2 going to be? It's going to be this length divided by r. Well, this length is just half of this length. In other words, this length is half, this length here is half of BC, but BC is just chord alpha. Okay, so then this is going to be 1/2 chord alpha divided by r. Okay, and so this gives a relationship between the sine function and the chord function. And of course, from this, we can directly figure out a relationship between the chord function and the cosine function, but maybe there's better ways to express it as well. Okay, so this is the relationship between the sine function and the chord function. Let's see if we can look, what we're going to want to build up to is we want to sort of give a table for every alpha, we want to be able to compute what chord alpha is. Just kind of not from going out and making a measurement, but by sort of doing things what we might call analytically, or kind of straight edge and compass type of things, right? So we're not just going out and measuring it, but we want to compute a table where we have exact values for all of the for chord alpha for all of the alphas, or for some set of values. So one of the things that we could do is maybe there's a way, if you know chord alpha for some angles, we can use that to figure out chord alpha for other angles related to alpha some way. Like if we do something to alpha and we know chord alpha, do we know what chord of this new angle is? So let me explain what I mean here. So let me take this line here, and I'm going to draw a diameter through the circle. So a line going from C through the center of the circle, which I'm going to call O, like this. So we're looking at the line CO, where it intersects the other side of the circle, and I'm going to call this A. Now, if I've done everything together, if I've done everything correctly, which I clearly haven't, things are, my drawing here is not exactly correct, this will be a horizontal line. AB here is going to be a horizontal line. Okay, now let's think here. So what is the relationship between AB and chord alpha? What is the relationship between all of these various things that we have going on here? So let's think about it like this. This angle, this line right here is a straight line. This angle here is alpha. So what it means is this angle here is equal to 180 degrees minus alpha, because to go from there to there is 180 degrees. This is alpha degrees, so then this angle here has to be 180 degrees, or 180 minus alpha. Okay, so now let's look at it. So AB is equal to chord of 180 minus alpha. So AB is equal to chord of 180 minus alpha. Okay, now let's look to see how things are going to go. Well, again, if I've drawn everything correctly, which I haven't, and I will let you explain why this is true, that's a right angle. Okay, now this length from there to there is r, and the length from there to there is r. Okay, so now I have a right angle where one of the legs is chord of 180 minus alpha, one of the legs is chord alpha, and then the hypotenuse is going to be r plus r, so 2r. So what I know then is chord of 180 minus alpha squared plus chord of alpha squared is equal to 2r squared or 4r squared. Okay, and now we can see how we can figure out from this, we can just solve this for chord of 180 minus alpha and take a square root. And this is going to give us what the chord of 180 minus alpha is. So in other words, this gives us a relationship between chord alpha and chord 180 minus alpha. And they knew how to take square roots. They knew at least how to estimate square roots up to any precision that they wanted to. So this is something that they were happy with because they could now, if they knew what alpha was, if they knew chord alpha, they could now figure out what chord alpha is, chord 180 minus alpha is up to any precision. Okay, so if they know what alpha is, they know what chord alpha, if they know what chord alpha is, they can figure out what chord 180 minus alpha is up to any precision by using this formula here and taking square roots. Okay, so what does that let us do? Well, if you know the angles if you know all of the chords from 0 to 90 degrees, then you automatically are going to know all of the chords for degrees going from 0 to 180. Because if you have something that's bigger than 90 and less than 180, you can just write that as 180 minus something that's going from 0 to 90. Okay, so and then similar things if you want to look at angles that are bigger than 180, there are similar things that you can do, of course. Okay, so then what this tells us then is if we want to develop a chord table going from 0 to 360 degrees, that is, in principle, for every number between 0 and 360, we want to be able to compute the chord. We just have to focus on going from 0 to 90 degrees. That's one thing that tells us. Then obviously this is going to be a good functional relationship that helps us compute other things as well. Just like it's helpful that sine squared plus cosine squared is equal to 1. It's true, but that fact also lets us do a lot of other things as well. Okay, I'm going to end this video here, and in the next video, I'm going to give a proof of this sort of like half angle formula for chords that's given in the book.